Hello and welcome to another episode of Mr. Boskin Talks About Math. Today we are doing Illustrative Math, Grade 8, Unit 8, Lesson 6. This is going to be our first lesson really diving into the Pythagorean theorem, which is one of the major topics of this unit. Our warm-up question here is a which one doesn't belong. There are 4 triangles here, and the question is which one doesn't belong. Well, looking at these quickly, I notice these 3 all have a side length that is an irrational number. It's a square root that doesn't have an integer answer, irrational numbers, so maybe this one's the odd one out. Or the other big piece that I notice is this is a right triangle, this is a right triangle, and this is a right triangle, and this is the only one that is not a right triangle. Okay, this says to complete the table for these 3 triangles. Triangle A, B, C So for each of these 3 triangles, triangle D, triangle E, and triangle F, we want to find the length of side A, side B, and side C, as well as the area of side A, side B, and side C square that you can use to find the side length. So triangle D, side length A is just 2 units. The area A squared, if we were to draw the square off from side A, that has an area of 4 units. Side B is a little trickier. How long is side B? Well, for this one, we kind of need to draw our square. So if we use this side length, side B, and draw a square off side B, we can then find the area of that square. This outer enclosing square is 2 by 2, so it would have an area of 4. Each of these outer triangles is 1 by 1. 1 times 1 is 1, over 2 is 1/2. So the area of those outer ones is 1/2 plus 1/2 plus 1/2 plus 1/2, which is 2, which means the area of this square is 2. If we know the area of a square to find its side length, we take the square root. So the length of side B is the square root of 2. C, we are going to have to draw the square off from side C. If we look at side C, it goes down 1 over 3. So coming away from that, we are going to want to go up 3 over 1. Up 3 over 1. And then this side will also be down 1 over 3, just like side C was, because they are parallel. So to find the area of side C, this is a 1, 2, 3, 4 by 4 box around it. These pages will start to get cluttered, but that's 4 by 4, so it has an area of 16 square units. Each of these side triangles is 3 by 1. 3 times 1 is 3, over 2 is 1.5. 1.5, 3, 4.5, 6. So that is an area of 6. So the area of this square, square C, is going to be 10 square units. So the side length will be the square root of 10 units. Now for E, A is again 2 units. Side length A is again 2 units, and the area of the square off of that will again be 4 units. Side B is 1 unit. 1 squared is 1 unit. Side C will be another one that we are going to have to draw our square to find the area. This side C is down 1 over 2, so we are going to want to go up 2 over 1 to draw our square, up 2 over 1 to draw our square. So here's the square that is the area of C squared. Now we want to enclose it again. That is 3 by 3, which is 9 units. Each of these triangles around it is 1 unit by 2. 1 times 2 is 2. Over 2 is 1. 1, 2, 3, 4. So the area of those outer triangles is 4. Subtract those. 9 subtract 4 is 5. So the area of square C is 5 square units. Once we know the area of the square, to find the side length of the square, we take the square root of it. The square root of 5 is not a rational number, so that side length is the square root of 5 units. Triangle F. Side A, still 2 units. 2 squared, still 4 units. Now, the length of side B and side C seem to be the same because this is a isosceles triangle. Now, coincidentally, we can draw this square, or we already know that if a length goes down 1 over 2, this is the square we would be drawing. We've already done this. This square is the same as this square, which means it has an area of 5 units and a side length of the square root of 5. Side C is the same. That will be 5 units, and this will be the square root of 5. What do you notice about the values in the table for triangle E, but not for triangle D and F? Okay. So E this one has 2 integer value side lengths and 1 irrational number, whereas both of the other ones have two irrational numbers. Let's look at these. What do we notice here? These are all nice integer values. F is the only one where two of the side lengths are the same. The other big piece I notice about this is that 4 plus 1 is equal to 5. That doesn't work for any of the others. 4 plus 5 doesn't equal 5. 4 plus 2 doesn't equal 10. But 4 plus 1 equals 5. Our next question is the same problem repeated but with 3 new triangles. I'm going to look for things we can fill in quickly. A on each of them is 2, much like it was on the last ones, which means A squared will be 4 for each of them. B right here on triangle P on our first one is the same 1 unit by 2 units that we did earlier, and the 1 unit by 2 unit triangle had an area of 5 and a side length of the square root of 5. So I'm going to fill in those quickly. So B, the side length was the square root of 5. The area was 5. Side B on this triangle is just 3 units. 3 squared is 9 units. Okay, I think those are all of the easy ones. Now let's look at side C on our first triangle here. This goes down 2 units and over 3, so we're going to want to go up 3 and over 2 because we do the inverse of that. That was not a great line. That gives our square off from side C. Enclose that square. And it is 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. That has an area of 25 square units. This little triangle off from it is 2 units by 3 units. 2 times 3 is 6. Over 2 is 3. There are 4 of them, 3, 6, 9, 12 units. 25 subtract 12 to get the area of our inner square is 13. So the area C squared is 13, which means our side length will be the square root of 13. Okay, for triangle Q here, side C is again 2 units by 3 units, the same as this side C was, so it will have an area of 13 and a side length of the square root of 13. Okay, triangle R goes down 3 over 1, so we are going to want to go up 1 over 3. Up 1 over 3. Uh-oh, we don't have space to do that one. Let's do B here, which goes up 3 over 1, so we would want to go over 3 and down 1. over 3 and down 1. And that gives us our square off side B. I went over the triangle because that's the only way there was space on this graph. If we enclose that, it is a 1, 2, 3, 4 by 4 square, which is 16 units. The triangles around it are 3 units by 1. 3 times 1 is 3, over 2 is 1.5. 1.5, 3, 4.5, 6. 6 units of space for those. This is a 10 unit square. Both of those sides are the same because this is a isosceles triangle, which means both of those side lengths will be the square root of 10. So now we've filled in another table. What questions will it ask us about this table? What do you notice about the values in the table for triangle Q but not P and R? So again, triangle Q, what do we notice about this one? Q is, again, 2 whole numbers, whereas the other ones only have 1 whole number and 2 irrational numbers. Let's check what we wrote down about the last table. The sum of the squares was the same. So for this one, 4 plus 9 equals 13. That worked again. 4 plus 5 does not equal 13. 4 plus 10 does not equal 10. What do triangles E and Q have in common? Can I fit both of those on the page? Yes, I can. Triangle E and triangle Q. I'm even going to erase what we had there. What do triangle E and triangle Q have in common? Well, what I see them having in common is this. Triangle E and triangle Q both have a right angle, making triangle E and triangle Q both right triangles. They are both right triangles. Six point 3. Find the missing side lengths. Be prepared to explain your reasoning. Okay. Side A here is the square root of 8 units. Side B is congruent. This is over 2 down 2. This is over 2 down 2. Those two side lengths are the same. So side B will also be the square root of 8 units. And side C is 4 units. Okay, then this says, for which triangles does a squared plus b squared equal c squared? The square root of 8. So square root of 8 squared plus b squared, the square root of 8 squared equals c squared. That's 4 squared. Now the square root of 8 squared, square rooting and squaring are inverse operations. The square root of 8 times the square root of 8, those will cancel out. That is just 8 plus 8 equals 4 squared is 16. 8 plus 8 is 16. This one works. A squared plus B squared equals C squared. Okay. Here's another triangle for us. A is the square root of 10. B is the square root of 40. We need to figure out the length of C, which means we are going to need to do what we've been doing, draw a square off from it and find the area. This is up 1 over 1, 2, 3, 4, 5, 6, 7. So we are going to want to go down 7. 1, 2, 3, 4, 5, 6, 7, and over 1. Here we will again want to go down 7. 1, 2, 3, 4, 5, 6, 7 over 1. Double check that this does the same pattern. Up 1 over 1, 2, 3, 4, 5, 6, 7. That worked. So our other two were correct. Here is our square drawn off side C. Now we want to enclose that. And this is an 8 by 8 square. So it is 64 units for the outer square. Our triangles are 7 by 1. 1 times 7 is 7. Over 2 is 3.5. Times 4 is 14. Subtract those to find out the area of our inner square. 64 subtract 14 is 50. So the area of this is 50 units. So the length of side C is the square root of 50 units. Now it wanted us to find out what if A squared plus B squared equaled C squared again on this one. So for this one, the A is the square root of 10 squared plus B, which is the square root of 40 squared, equals C, which is the square root of 50 squared. Squaring and square root are inverse operations. They cancel out. That is equal to 10 plus 40 equals 50. 10 plus 40 equals 50. Yes, that works. Okay, we have one more triangle here. C is the length of side C is 5. The length of side B is equal to the square root of 17, and side A right here is 1, 2, 3, 4 units. So now we want to again find out if A squared plus B squared equals C squared. A is 4 squared plus B square root of 17 squared equals C squared. 4 squared is 16. The square root of 17 squared is just 17 because inverse operations cancel out, equals 5 squared, which is 25. Does 16 plus 17 equal 25? No, it does not. So that one did not work. So let's look at these again. Triangle P, which was a right triangle. A squared plus B squared equaled C squared. Triangle Q, which was again a right triangle. A squared plus B squared did equal C squared. And triangle R, which was not a right triangle. A squared plus B squared did not equal C squared. So this is going to be one of our big building blocks of the Pythagorean theorem. The "Are you ready for more?" question says, if the four shaded triangles in the figure are congruent right triangles, does their inner quadrilateral have to be a square? So if these shaded triangles are congruent and they are right triangles, does the inner quadrilateral have to be a square? So how can we tell if this inner figure has to be a square? Well, to be a square, there are two requirements. The side lengths all need to be congruent to each other. This side, this side, this side, and this side are the hypotenuse of each of these triangles. It says all four shaded triangles are congruent, so those four sides, which are all the hypotenuse of their respective triangle, need to be congruent to each other. Now, we need to find out, are these angles right angles? Well, we know that this figure here makes a straight line, which means the sum of these three angles has to be 180 degrees. We also know that if these triangles are all congruent, if I call this triangle as having angle 1, angle 2, and angle 3, we know angle 3 is a right angle because we know these are congruent right triangles. So we know angle 3 is a right angle. We also know that if these triangles are congruent to each other, if this is angle 2, on this triangle here, this is our angle 1, this is our angle 2, and this is our angle 3. We know that's a right angle. And we know angle 2 has to be congruent to this angle 2 because the triangles are all congruent to each other. And we know the angle sum of a triangle is 180 degrees. And we know the angle sum of this is 180 degrees, which means angle 1 plus angle 2 has to be 90 degrees. Because in this triangle, angle 1 plus angle 2 is 90 degrees, because angle 3 we know has to be 90 degrees. So this has to be the same as angle 3. So if this is a right angle, all four of these angles need to be right angles. The sides are all congruent. So this figure, inner figure, must be a square. Our quick summary of lesson 6. A right triangle is a triangle with a right angle. Here's a triangle with a right angle. The side opposite the right angle is called the hypotenuse. This side here, which is opposite the right angle, the only side that's not touching the right angle, is called the hypotenuse. The other two sides are called the legs. This is a leg, this is a leg. Here are some right triangles with the hypotenuse and legs labeled. right angle, hypotenuse. Right angle, touching the two legs, hypotenuse is opposite. Same thing in all of these spots. We often use the letters A and B to represent the shorter sides of a triangle and C to represent the longest side. So whenever we're doing this, A and B will be the shortest side and C will be the longest side. The side opposite the hypotenuse of a right triangle will always be the longest side. For example, in this right triangle, A equals the square root of 20, B equals the square root of 5, and C equals 5. Here are some more right triangles. Dimensions are labeled. Notice that for these examples of right triangles, the square of the hypotenuse is equal to the sum of the squares of the legs. 9 plus 16 equals 25. 1 plus 16 equals 17. 9 plus 9 equals 18. This is a property of all right triangles, not just these examples, and it is known as the Pythagorean theorem. The name comes from a mathematician named Pythagoras who lived in ancient Greece around 2500 BCE. But this property of right triangles was also discovered independently by mathematicians in other ancient cultures, including Babylon, India, and China. In China, the name for the same relationship is the Shanggao theorem. In future lessons, we will learn some ways to explain why the Pythagorean theorem is true for any right angle triangle. It's important to note this relationship does not hold for all triangles. Here are some triangles that are not right triangles, and notice that the lengths of their sides do not have the special relationship a squared plus b squared equals c squared. 16 plus 10 does not equal 18. 2 plus 10 does not equal 16. This is a special relationship that only holds for right triangles. The Pythagorean theorem, a squared plus b squared equals c squared, only holds for right triangles. This has been another episode of Mr. Boskin Does Some Math. Thank you for tuning in. See you next time.